Hello everyone, this is Thomas Preußer. I'd like to present to you our work on using FPGA DSP slices for implementing fully associative content-addressable update queues. This talk will give a quick review of CAM emulation options on FPGAs, describe our considered use case, our DSP-based solution, and our achieved experimental evaluation results, before closing with some conclusions. Content-Addressable Memory, for short CAM, is a functionality required by many application contexts. Classic memory caching, interface lookup for network packet routing, and hazard detection for concurrent accesses to memory or other resources. While modern FPGAs comprise various special-purpose structures, native associative CAM is not among them. Thus, its functionality has to be emulated. The relevance for this functionality is stressed by major vendors providing IP cores for its implementation. Particularly, key slicing has been shown to make CAM emulation using block and distributed memory feasible with a bearable space overhead. Our goal is to bridge the long read latency of off-chip memory that we use to maintain large event occurrence statistics. In order to facilitate continuous event processing, stalling is not an option to resolve read-after-write hazards between close updates on the same event. Instead, we would like to aggregate all occurrences on an event with a pending read-modify-write cycle and then use the so accumulated increment for computing the value to write back. For this, a fully associative CAM mapping events to their pending accumulated updates is needed. Its capacity must match the read latency of the used off-chip memory of 100-200 cycles. Again, associativity conflicts cannot be tolerated. However, we may want to exploit the fact that update cycles are initiated and settled in FIFO order. As can be seen here, the FIFO order allows us to organize the associative update aggregation as a queue. The event aggregation is achieved in a decentralized manner based on the local match result. Every event or key within the queue is unique. Only events admitted to the queue initiate a memory update cycle. As they reach the end of the queue, their aggregated increments are applied to the received memory replies and written back. Fully associative matching of new event occurrences requires parallel comparators across the whole depth of the queue. Besides its structural size, the aggregation feedback from the many comparators telling whether or not a new event input has been matched establishes a challenging high fan-in computation. While DSP slices are best known for their multipliers, they also provide key functionality for implementing our aggregation queue. Particularly, we can map the storage for both event keys and increment values, the comparators, and the aggregation arithmetic. This frees valuable general-purpose fabric resources. In particular, predictable, designated internal DSP slice routing can be utilized for the data path. Note that the parallel event matching and aggregation is distributed across two adjacent DSP slices here to account for their registered comparator output. Combining all the comparator results for an instant global match decision does not scale to hundreds of comparators. However, this feedback path can be pipelined as shown in this figure. The decision of admitting new inputs that have identified as unique must be retimed accordingly. Unfortunately, the events in the implied input delay stages have an undecided fate and are not safely available to subsume identical follow-ups. Consequently, a pipelined aggregation feedback requires identical keys to have a minimum spacing in the input stream that matches the number of added pipeline delays. An end-to-end solution that can both process an unrestricted event stream and cope with the full memory latency can be built from subsequent stages of aggregation queues. A sensible stage schedule would start with a short queue with a combinatorial aggregation feedback, so as to avoid any requirements of input key spacing. This stage establishes a key spacing that allows the subsequent stage to use a pipelined aggregation feedback. It can thus be deeper and achieve a wider spacing. Queues are chained until the last one matches the memory latency. For the experimental evaluation of our approach, we ran a minimal application on a VCU 118 prototyping board. It features a VU9P device and onboard RLDRAM3 memory with advantageous random access properties. We use the factory tool settings and memory controller. We profile a random event stream into more than 16 million buckets. We allow for non-intrusive, consistent statistics snapshots, which demands a secondary shadow increment path. All the 24-bit event key, its associated valid flag, and two 10-bit increment lanes for up to 1,000 aggregated close-by occurrences can be accommodated on the internal DSP data path. We compare our DSP mapping against an aggregation queue implemented solely with Fabric resources. Both implementations achieve competitive timing well above 300 MHz. With appropriate aggregation schedules, the queue approach scales well to deep depth, as demonstrated by the 3-stage schedule, achieving a final minimum spacing of identical keys by 1,000 intermediate cycles. The design matching our system requirements comprises 2 aggregation stages with a final key spacing of 250 running at 375 MHz. It matches the practically achievable memory bandwidth of 750 megatransactions per second. For its fully associative CAM operation, it has to perform more than 90 billion key comparisons per second. The key trade-off we offer to a designer is the choice between using DSP slices versus general-purpose Fabric resources. Each invested DSP slice frees about 40 Fabric registers and up to 30 lots for well-amortized stage control overhead for deep schedules. In conclusion, we have achieved a non-blocking, fully associative aggregation CAM for collecting off-chip statistics. We demonstrated how DSP slices can combine CAM storage, key matching, and increment aggregation. We quantified the resource trade-off between using DSP slices versus Fabric resources, and established DSP slices as another potential CAM emulation resource on FPGAs. Thank you very much for your attention.